Okay, so the next topic we want to cover is regular solutions. And regular solutions is a theory where we consider um, the effect of non-zero enthalpy of mixing on a solution. So remember, in the ideal solution, we considered delta H of mixing to be 0. So in this case, we're going to make a few assumptions. So let's try to make our assumptions clear. So for the regular solution, we're going to assume pairwise interactions between atoms in the solution. We're going to assume that there's a given coordination number that is how many atoms any given atom interacts with, Z. So that's essentially like the number of neighboring atoms. We're going to assume that the interactions are limited to these neighboring atoms, and that the interaction energy only depends on the species interacting. In particular, that it doesn't depend on the concentration of the solution in which the species are interacting. And also that the probability of a site being occupied by a species of type I depends only on the concentration of that species, so of I atoms. And furthermore, we're going to assume that delta H of mixing, the enthalpy of mixing, is approximately the energy of mixing, or in other words, that P delta V, the effect of changes in volume, is much, much less than changes in enthalpy. So that the energetic change is the biggest contribution to the change in enthalpy. And that's generally true for condensed phases, like solids and liquids. Okay, so those are our assumptions. So where do we go from there? Well, we want to figure out an expression for this enthalpy of mixing, right? So we're going to start by considering the enthalpy of mixing. So for a pure component, if we just had component 1, right, for pure component 1, the energy of the system would be given by, we'd have a number of bonds that would be proportional to the number of atoms, right? So the number of atoms of type 1 times the coordination, right? So if you had 8 nearest neighbors, you'd have 8 bonds, but those bonds are shared between 2 atoms. So each one of those bonds per atom only would contribute a half of the energy associated with a bond between 2 type 1 atoms to the system. So a good expression for the energy of a pure type 1 system would be this, where the 1/2 is avoids double counting. Okay, so now let's consider what happens if we have a solution, right? So if we have a solution, so then we have the atoms of type 1, they have interactions with other atoms of type 1, and the number of those we should expect is proportional to the coordination number times the number fraction of type 1 bonds, and they may contribute to the energy due to neighbors that are of type 2, and the fraction of those we should expect would be the coordination times the mole fraction of type 2. And then we have the contribution of the species 2 atoms, and those would contribute a bond of energy 1, 2, proportional to the coordination number times the concentration of species of type 1, plus energy of bond of type 2, 2 times the coordination number times the concentration of type 2. So that's the energy of the system, and our enthalpy of mixing, delta H mix, we defined as the energy of the solution minus the energy of pure 1 minus the energy of pure 2. So that would give us, let's start multiplying this out, right? So we're going to have 1/2 N1 ZX1 epsilon 1, 1 plus 1/2 N2 ZX2 epsilon 2, 2. That comes from this term, plus 1/2 N1 ZX2 epsilon 1, 2 plus N2 ZX1 epsilon 1, 2. Okay, so that's from our US, and then we have to subtract from that minus 1/2 N1 ZX or Z epsilon 1, 1 minus 1/2 N2 Z epsilon 2, 2. So what minus the contributions we would get if the N1 and N2 atoms were completely separated from each other. Okay. So our delta H mix for the epsilon 1, 1 contribution, we're going to get, or let's look first at the epsilon 1, 1 contribution. So we're going to get minus 1/2 N1 Z X2 epsilon 1, 1, right? Because we're going to have 1 minus X1 gives us X2. And we're going to get a minus 1/2 N2 Z X1 epsilon 2, 2. Okay, subtracting these off, and then we get this cross term, which remains the same, but I'll write this as 1/2 N1 Z X2 epsilon 1, 2 plus 1/2 N2 Z X1 epsilon 1, 2. Okay, and now I want to combine the contributions from type 1 atoms and the contributions from type 2 atoms, so I can say N mix is 1/2 N1Z X2. Okay, so this is our N1 X2 contribution, and that's going to give us epsilon 1, 2 minus epsilon 1, 1 plus 1/2 N2 Z X1 epsilon 1, 2 minus epsilon 2, 2. Okay. Or another way of writing this would be to say delta H mix is equal to Z over 2, right, times, and here we have N1, N2 over N. So here I'm just multiplying and dividing by N. N times X2 gives us N2, so this gives us N2 over N, and this gives N1 over N. So this is the same prefactor for both, and then we get epsilon 1, 2, or 2 epsilon 1, 2 minus epsilon 1, 1 minus epsilon 2, 2. And that's our sort of compact expression for the delta in the enthalpy of mixing. Okay, so we can combine that into an empirical constant. So we're going to call B12 is equal to Z times n number of atoms over 2 times 2 epsilon 1, 2 minus epsilon 1, 1 minus epsilon 2, 2, and then delta H of mixing. So this is just an empirical constant that just depends on, or Na is Avogadro's number, sorry. And then we can say delta H mix is just equal to B12, which is some empirical constant, times the number of moles of 1 times the number of moles of 2 over the number of moles of 1 plus the number of moles of 2. Or in other words, B12 times total number of moles and times x1 times x2. Okay. So this gives us an expression for delta H mix, and now we want to write down the free energy for the whole system, G, and we're going to say that G, the free energy, is just going to be equal to the ideal free energy. So we want to include the contribution from entropy that comes from the mixing from the ideal solution plus the enthalpic term, which the ideal solution ignored. So this is going to be just G ideal plus B12 times N1, N2 over N total. So if we calculate from that, for example, mu1, which would be the chemical potential of species 1, that would be given by dGdN1 at constant N2, so that would be given by the ideal chemical potential for 1 plus a correction that goes like B12 times N2, N1 plus N2 minus N12 over N1 plus N2 squared. So here we're just taking the derivative of this with respect to N1. Right? This is N1 plus N2 in the denominator. So we get at the end of the day mu1 is equal to mu1 0, right, plus RT natural log of x1, that's our ideal contribution, plus B12 times x2 squared. Okay. And so if we were to think of B12 in terms of our activity coefficients, we can see that this has to equal RT natural log of gamma 1. So in terms of B12, gamma 1 is equal to exponential of B12 x2 squared over RT. Okay, so next we'll think about what this all means. So now we have the mathematical formalism, we can look at the regular solution.